Welcome back. This module is on understanding the operational amplifier as an integrator and as a differentiator. So, what you mean by integrator, right? So, first we have seen what you mean by op-amp, operational amplifier, it performs several operation. What do you mean by integrator? Integrator means it will integrate lot of things in one, it will integrate. But if I talk about differentiator, it will cut it, it will differentiate into lot of fragments, differentiator. So, understand from the meaning point of view first, and then you understand the actual role of the operational amplifier as an integrator or a differentiator, all right. So, if I tell you how to use operational amplifier as an integrator and what is the formula of an integrator, or how can we derive this formula of an integrator. Since integrator and differentiators are very easy to derive, the formula of the output voltage or the output voltage of integrator and output voltage of differentiator is extremely easy to derive. We will see quickly how we can derive this integrator and differentiator, and then we will perform several experiments and see when we apply different input signals, right, what are the output signals corresponding to those input signals. And you will see that okay, if you want to convert your sine wave to a square wave or rectangle wave or triangle wave to sine wave to triangle wave, and lot of other changes of the signal you can change the signal by using this particular circuits. So, when you talk about the integrator, let us first see what exactly a integrator means. So, what we have seen until now, we have seen that there is a feedback resistor RF, right. We have not seen this, we have seen RF, and if this is the case, it is your inverting amplifier, it becomes your inverting amplifier, right. Now, if you replace this RF by a capacitor, it becomes your integrator. So easy, extremely easy, right. So, how this works as an integrator? How you can say that by replacing RF by capacitor C, feedback resistor by capacitor, it becomes an integrator. So, let us see. It is same thing is written. First point, by replacing the feedback resistance with a capacitor, we get a RC network connected across the operational amplifier feedbacks path, producing another type of operational amplifier circuit called op-amp integrator, all right. So, if you replace RF by C, it becomes an integrator. Let us see how. So, let us see I in, this value I in and this value I f. So, I in is equal to I f, this is easy, right, your I in is equals to I f, right. Now, what is I in? I in is nothing but, you see you have resistor R in, you have voltage V in. So, what will be I? I will be, you have V in minus V upon R in. What is V? V is some Vx, some Vx voltage here, all right. So, you understand V in is nothing but V is nothing but Vx, all right. So, if you want to consider I in, you have to take the difference. So, V in minus Vx divided by R in, okay. This is easy. If I want to consider If, what will be If? C into dV by dt, right, C into dV by dt, this is the formula. Now, what is V here? V is nothing but Vx, we can say V or Vx. So, I say Vx minus V out upon dt, all right. Now, you see here we have seen a concept of virtual ground in the theory class, right. What does that virtual ground means? If I want to consider voltage here, my voltage Vx would be 0, voltage Vx would be 0. So, if I substitute Vx equals to 0 in this equation, then what will I have? V in upon R in equals to minus C dV 0 by dt, right, or minus dC dVO by dt. So, from here if I want to find VO, what will be? I have what will I have? VO is nothing but integration of V in dt, and here will be minus 1 upon RC, minus 1 upon RC, and the time is from 0 to t, time is from 0 to t. So, very simple, right. If I want to have VO from here, VO, right, we have to say bring it here. So, it is minus 1 by RC, right, RC is what? R in. So, R in into C integration of 0 to time t, right, into V in into dt, all right. So, this is the formula for your integrator, this is formula for your integrator. Now, this is the ideal situation, this is the ideal situation where you will put a capacitor C and you will have resistor R in and you will find everything working well. But in actual operation amplifier, when you use as an integrator, you will not find the ideal situation. That means that in that particular situation, the input offset voltage, which is for a non-ideal op amp, is not 0. We have seen input offset voltage, right. So, what is input offset voltage should be? Input offset voltage for ideal operation amplifier, ideal op amp should be 0, this we have seen, right. But actually, right, actually we have practical op amp. In practical op amp, we will see that the input offset voltage is not 0, all right. Also, that is why, which is now this is not 0, that means it is non ideal op amp, it also gets integrated, whatever the input offset voltage is there also gets integrated. As a result, the output voltage starts to drift, output voltage is it starts to drift. To fix this drifting, we have to add a feedback resistor RF. If you see in this circuit, we have added a feedback resistor RF. This will make the circuit, or this makes the gain for very low frequency signals finite again, all right, and this is what we have shown here in the figure 5, right. So, let us see once again what we have been discussing. In the case of integrator, there is only capacitor in the feedback and there is a resistor at the input. But if the op amp is ideal, then an integrator would require just one R and one C, all right. But in reality, op amp is not an ideal op amp, and if it is not ideal op amp, then the output or the input offset voltage would be not equal to 0. When it is not equal to 0, then your output voltage would start to drift, right. So, when your output voltage starts to drift, how to fix this drift? We can fix this drift by adding a feedback resistor or by adding a resistor RF across the capacitor, all right. This will help or this makes the gain for very low frequency signals finite, and thus it will help to reduce the drift, all right. It will help to reduce the drift. This is the case of an practical operational amplifier used as an integrator, all right. So, remember this, all right. We will perform the experiments, remember this what we have discussed for integrator, all right. Now, let us go to the next one, and what do you see? You see the figure of an differentiator. So, look closely at figure 6 and think what is the difference between integrator and differentiator in terms of circuit. Look at it, understand, and I will ask you in 10 seconds, see what is the difference between integrator and a differentiator, right. Your time starts now, 10 seconds. Three, 2 and 1, all right. So, what is the difference? Very easy, right, all of you got it. What we have done here? Here instead of R in, we have changed by C, right. In case of integrator, what we did? We have changed RF by C. In case of differentiator, we have converted R in by C. Easy, extremely easy. So, you cannot forget this circuit, you cannot forget this circuit because it is super easy to remember. Integrator, feedback, capacitor, differentiator, input, capacitor. Alright, the input signal goes to the capacitor. In integrator, the feedback resistor is replaced by the capacitor. To reduce the drift, we use the feedback resistor across the capacitor. In this case, let us see how the differentiator would work. Okay. So, let us come back to the circuit. What we see here, in the differentiator, the position of the capacitor and resistors are reversed as shown in figure, right. The answer is already here. Now, the op amp circuit performs the mathematical operation of differentiation. We all know mathematics, we have all studied mathematics, what is differentiation, what is integration. So, if you want to perform this mathematical operation of a differentiator of a differentiation, then we can use this circuit which is shown in figure 6. Alright. Now, if you see figure 6, this particular circuit produces a voltage output which is directly proportional to the input voltage rate of change with respect to time, right. This is what differentiator does, right. See, the output voltage is directly proportional to the input voltage rate of change with respect to time. All right. That means that you will see, you will find the equation similar to what we have done in the integrator. Let us find out the equation. First, let us understand further. So, that is second what we have understood. Let us see once again quickly. First point is position of capacitor and resistors are reversed in case of differentiator when you compare with integrator. Second point is it can perform mathematical operation called differentiation. Third point is the output voltage is directly proportional to input voltage rate of change with respect to time. Fourth one is, in other words, the faster or larger the change of the input voltage signal, faster or larger the change to the input voltage signal, the greater input current, the greater the output voltage change in response, becoming more spike in shape. We will see this so that you can understand what exactly we mean by this particular sentence, right. For now, you just understand that if you have a faster or larger change of input voltage signal, then you will have greater input current, and this will cause the output voltage change in response in terms of a spike signal. Will result. We will see this in actual experiment, and then you will understand. So, how we can derive this equation for the differentiator? What is a way of deriving the equation for the differentiator? So, what we see here is that if I apply Kirchhoff current law, see I use this Kirchhoff voltage law, Kirchhoff current law many times I have used in the theory class, right, and in last module also I have used Kirchhoff voltage law or Kirchhoff current law. When I use this thing, you should go back and understand what exactly Kirchhoff current law is, what exactly Kirchhoff voltage law is. Once you understand, then it will be easy for you to understand how this thing we can write in this particular fashion. Alright. So, if you understand Kirchhoff current law, understand Kirchhoff voltage law. Now, let us see that if we have this circuit, then we can write C into dV, this particular one, C into dV in by dt equals to nothing but this one, if you see, minus VO by RF, So, the output, if I want to calculate, which is voltage, V of is nothing but RF will go here, minus RF into C into dV in by dt. It is very easy, right. Understand Kirchhoff current law, you will understand this part, you understand this part, then you see that this is equal to this, and then from that we apply voltage. We want to find the output voltage is nothing but VO, which is equals to minus RF C into dV in by dt. Alright, easy, it is extremely easy. So, now let us see the next one. So, here what we have seen, we have used a P-spice, and using P-spice we have formed the differentiator amplifier, which is shown in the slide. Here we have applied the voltage, and correspond to the input voltage we have measured the output signal. We will do the similar kind of experiment on the breadboard, right. This experiment was done by Sitaram, and this signal the circuit he has drawn in PSpice using PSpice, and he found this interesting observation. This slide was specially prepared for you guys, so that you can understand how the input signal varies and how the output signal will vary with respect to input when you take a case of a differentiator. Alright. So, you see here that input signal and output signal, right, how they are related in case of a differentiator. First is when you apply square wave, you will be able to see spikes. If you apply triangular wave, you can see rectangular wave. If you apply sine wave, you can see cosine wave. That means that you can use the differentiator as a signal converter, right. If you want to get a output signal as spike, and if I give output as a input as a square wave, then I can get spike. So, where I can use spike, that is a different case. Where I want to use the rectangular wave, it is a different case. Where I want to use cosine wave, it is a different case. Right. But the point is that you can also do the similar kind of study using PSpice and understand and perform the experiment if you do not have a breadboard with you. If you do not have DC power supply, if you do not have other things, you can use this tool and you can perform the experiments as well. Alright. So, this is a different way of understanding the experimental approach to the theory. Alright. So, now we will see we will try also actually do this same study, right. We can see here these are reference voltages or bias voltages, this particular is an op amp, right. You have a resistor here and you have capacitor here, right, as a in the input. Now, you see when we apply this signal, if we apply a square wave, we will actually perform the experiment and we will see whether we can obtain these spikes or not. Alright. If we apply triangular wave, whether we can get this rectangular wave or it is just PSpice shows something and actual experiment shows something, right, we will cross check it. Alright. So, if I compare the differentiator and integrator, right, if I compare differentiator and integrator, what I find? You see here I have differentiator, I have integrator, right, and here like we have seen in the last slide, I give different signals at the input, I get different signals at the output. What about integrator? What about integrator? If I apply input which is in this particular fashion, my output is this, which is a triangular wave. I can make a triangular wave. If I input is rectangular wave, I can make a triangular wave, or square wave I can change it to the other signal, right. Same way sine wave I can get cosine wave with integrator as well. So, the role is, the point is that by using integrator and differentiator we can convert the signal, one. Second is we can integrate or differentiate the signal, that is it can be used as a mathematical operation. And third point is that how we can use op amp as an integrator and differentiator in actual experiments. So, let us see now, if I want to cross check or if I want to understand the property of an operational amplifier as a differentiator, what kind of experiment I can perform. Alright. So, before we move to the experiments, let us quickly see the problem. Alright. What is the problem? So, problem is not really a problem, it is a question to which we have to find the solution. There is no problem with the course, no problem with these slides, do not worry about it. So, if in this particular figure which is figure 7, what is this figure? This is a figure of an integrator, alright. The op amp saturation voltages are plus 12 minus 12, that means here if some, I have told you earlier also, if we do not see plus VCC and minus VCC, that does not mean that we do not have plus VCC minus VCC, alright. It is not mandatory to show every time bias signal. The resistance R is 10 kilo ohm, R is 10 kilo ohm, 10 kilo ohm, C is 0.01 millifarad, 0.01 millifarad. If at t equals to 0, at time t equals to 0, we apply voltage 7.4 volts. So, at t equals to 0, V equals to 7.5 volts, this V, this V1, right. What we have to determine? Determine value of output voltage at t equals to 100 microseconds. So, this is given at t equals to 100 microseconds, what is output voltage VO, alright. This is the question. So, let us see how we can find the answer or I can find the solution. So, now we already know, if you see the circuit, right, what we know? We know that VO equals to delta VO by delta T equals to minus VI by RC. So, if I substitute the value here, I have 7.5 volts as input voltage here, divided by R is my 10 kilo ohm, C is 0.01 millifarad or 0.1 microfarad. Is it microfarad or millifarad? So, I think let us consider microfarad, let us consider 0.1 microfarad, C equals to 0.01 microfarad, then I will get this particular value. Alright. The change in output voltage is given by delta VO equals to minus 75 millivolts by microsecond into delta T. What is delta T? Delta T is nothing but at 100 microseconds what is the change. So, when I multiply this, what is my delta VO? Delta VO is minus 7.5 volts. That means that if we assume that T equals to 0, the output voltage V 0 equals to 0, then after 100 microseconds the output voltage is VO equals to minus 7.5 volts. Alright. So, again you can see this same thing in this particular circuit. See the circuit, there are both the signals, you can see signal 1, signal 2, understand how the input signal is there, how you get the output signal, and this is the easiest way of understanding an integrator by taking our input voltages, understanding what will be the output at T equals to 100 microseconds. You can change this value and find a 200 microsecond, 300 microsecond, 10 microseconds, and you can also put this value in your actual experiment and see what happens. Alright. So, let us see one more, let us now actually perform the experiment which is of an integrator, right. So, we have seen that in the actual integrator or in the practical op amps, we have to use the RF, right, to remove the drift. We have seen that, correct, because if we do not use RF, then we will see the drift in the output voltage, and to remove this drift the RF would help. So, let us see whether it is helping or not, that is the question. Alright. So, first connect the circuit as shown in figure 8, we will connect the circuit exactly in this particular format, apply V in as a square wave. So, we will apply V in as a square wave. Alright. So, you can form square wave when we understand that if this is 0, right, which is here, this is your time t and this is your amplitude or you write V 0. So, when you draw it, draw perfectly like this, alright. If you want to draw like this, then you can draw like this also, square wave, you can draw like this also, square wave, right. There are way of drawing the square wave, it is not like one way what heat is shown here is the right way. So, you can draw your square wave in your own format. The point is you should be square wave, that is only the point. So, what is the point? That we apply square wave, 1 volt, 1 volt, right, 5 kilohertz at the input. We have to observe the output voltage and we have to comment on the shape of the output waveform. That means, first is what is VO and second is what is the shape of the output. That means, if I apply square wave, what will be my output signal, alright. This particular experiment we have to perform. So, let us again connect this circuit and let us see how it looks on the breadboard and what kind of output voltage we obtain when we apply V in of 1 volt peak to peak 5 kilohertz frequency, alright. So, let us again call Sitaram and see the circuit. So, if you can see the circuit on the breadboard please. Alright. So, the circuit is, if you see focus here, if you can lift little bit, then this is the integrator. We are first looking at the integrator. You can see there are two resistors, right, resistors, and there is a capacitor. Here is a capacitor, there is a capacitor and resistor RF, and then there is a input resistor R in, right. One is a input resistor, one is a feedback resistor connected with the feedback capacitor, CF across it, RF is there, alright. Now, we are applying at the input a sine wave which is 1 volt, sorry, a square wave, let us see, square wave 1 volt 5 kilohertz, and at the output we have to measure the voltage VO, alright. So, let us see the function generator, and what he is applying right now. If you see, he has given square wave square wave at 5 kilohertz, at 5 kilohertz, peak to peak voltage is 5 volts, peak to peak voltage is 5 volts. Again you should immediately able to see when I say peak to peak voltage is from 0 millivolt to 5 volt on y axis, right, and the frequency is 5 kilohertz. So, on applying this one, what is output voltage? Let us see the output voltage please, output voltage on the oscilloscope. Okay. And if you zoom out, zoom in, sorry. Okay. Now, what we see, peak to peak output voltage is, can you please show where is the value? So, square wave that you see yellow color is the input, and output voltage is my 2.40 volt, is it? Yeah, 2.40 volt, and input voltage is 5.4 volts. So, and what I see at the output? You see what I see? I see a triangular wave, right. So, an application of a square wave at the output, I am able to see the triangular wave. This we can do with the help of an integrator. With this we can do with the help of an integrator. Now, let us change the signal at the input, alright. So, again go back to the function generator please. You see, if we apply sine wave, then we can, if we apply sine wave at the output, we were able to see cosine wave. At the output we are able to see the, if you see the output again at the oscilloscope, we are able to see the cosine wave, alright. So, when application of a sine wave. Now, let us apply another signal. So, if I apply triangular wave, if I apply a triangular wave at the input, right, I can see a sine wave. Is it sine wave? Let me see, it is almost similar at the oscilloscope please. Okay. So, almost a sine wave at the output, alright. So, the point is that I can get different form of signals when I apply different form of signals at the input. So, change it, see, observe what is the change in the output signal, alright. That is the exercise, that once I show, you see what exactly that is the change when I apply different input signal. Now, if you apply different input signal and see what kind of output you can see in the oscilloscope, alright. So, that is the experiment that we have performed. The output voltage is nothing but 2.4 volts, like we have seen 2.40 volts at the output, input was 5 volts peak to peak, and we were able to see that the output was a triangle, input was a sine wave or input was a square wave in one case like this, square wave, right, and the output was a triangular wave, alright. So, this is the case study where we have used operational amplifier as an integrator. How about we take a differentiator? How about we take a differentiator? Now, we all know the difference in the integrator, and differentiator is that we have replaced the R in by capacitor and RF is as it is, R in by a capacitor and RF is similar. This becomes your differentiator. So, if we consider the differentiator circuit, what we are looking at? We are looking at a capacitor, we are looking at R2, right, and we have another resistor R in the series, but the input signal is fed to the capacitor. So, if I apply V in of 1 volt, V in of 1 volt at 5 kilohertz, then what will happen? So, see, if you do not want to use this one, then also it is okay, it is perfectly okay, alright. So, do not worry, do not get confused that, oh, there is one more resistor in the circuit, do not worry, you can directly apply capacitor and you can have a feedback resistor R2, alright. So, if I apply 1 volts at the input here and I want to measure the output voltage VO, right, I want to measure output voltage VO, and then I will have to comment on the output waveform. That means, if I apply a square wave, again see in the integrator also we are applying, we may have applied square wave, in differentiator also we are applying square wave, and we are looking at the output voltage. Correspondingly, we are also looking at the shape of the signal, right. So, again we need to connect the circuit, and we have to understand what is the output voltage. One, what is output voltage VO. Second, what is the shape of VO on applying square wave at input. All right. So, let us see this. So, again let us focus on the breadboard, and let us see the differentiator circuit first. So, you can see the differentiator circuit. So, you can see here the differentiator circuit. Here we have the capacitor at the input, and we have a resistor which we have seen here, and then we have a resistor which is feedback. Now, we are applying the signal at the input. Before that, we have to apply the bias voltage to the operation amplifier, which will apply through the DC power supply. Then we have to apply input 1 volt peak to peak at 5 kilohertz, 1 volt peak to peak at 5 kilohertz. So, square wave 1 volts peak to peak 5 kilohertz frequency. So, let us see the first let us see the function generator please, and we will be able to see when you focus on function generator that the input voltage is 1 volt peak to peak 5 kilohertz. Okay. Now, we are applying this 1 volt at the input, and we are measuring the output of the differentiator. We are measuring the output of the differentiator. So, as you can see on the screen, right, when we apply the square wave at the input, the output results in a spike, spikes. So, let us see the voltage at the output. The voltage of the output, you can see the oscilloscope please, oscilloscope, yes. Okay. So, you see the voltage at the output is about 2 volts, when we apply peak to peak signal of 1 volts, 1.04 volts, right. Here the case is different. In case of integrator, when we are applying about 5 volts, we are observing 2.4 volts. Here we are applying 2 volts, we are applying input signal as 1 volt, and we are observing the output as 2 volts. But you see here, you do not have to only measure the output, you also have to comment on the shape of the waveform, and the shape of the wave is nothing but a spike. All right, it is a spike. Now, let us change it. That means that we give a different signal to the input. We have given a sine wave at the input, and at the output we are able to see a cosine wave. Let us give another signal at the input, which is the triangular wave, and you can see kind of square wave when you apply the triangular wave. All right. So, the point is again that you have two different circuit, one is differentiator, one is integrator. With both the circuits you can get different kind of waveforms at the output on application of the input signals, right. So, what we have to understand is that once we understand operation amplifier, we can use this operation amplifier as a different for different application. And today for this particular module, what we have seen is a differentiator and an integrator. And to quickly recap what we have seen in this particular module is, we have seen an integrator, then in the integrator the RF, which is a feedback resistor, is replaced by a feedback capacitor C, right, in the feedback, the back. And then what we found is, for the ideal situation is okay, but then there is a drift. So, to remove the drift, we put a resistor RF across the capacitor in the feedback, and then we have performed the experiments, and we have seen we have applied different signal, and we have seen the output at the integrator. Then we took a differentiator. The difference between the differentiator and integrator is nothing but the capacitor. Now, instead of in the feedback, it will be at the input of the differentiator. So, now you are applying the signal to the differentiator at the input, and you are measuring the output. Feedback, there is a resistor R, and here the input there is capacitor C. Now, we have a formula which we have derived, and we can see that on application of a square wave, the output is nothing but spike in case of the differentiator, but when you take a case of the integrator, then you were able to see a different output signal, right. So, what we find from this experiment is that you can perform the not only using the breadboard, but you can also do similar kind of study using PSpice, and you can find out whether you can see the change in signals or not. In case if you do not have the facility which I am showing it to you, you can perform the experiment right at your home using these tools similar to PSpice, all right. Again, you can use any tool that is good for you. It is I am not doing any marketing for PSpice. I am just telling you that this is one of the tool that you can use for understanding the operation amplifier, actual experiments of the operation amplifier, all right. So, with that there are more applications of operation amplifier, and in the following modules what we will be looking at, the following modules we will looking at the filter. It is an amazing application of an operation amplifier, and how it can be used to filter out signals. What is the role of filter, what kind of filters are there, and we have to see how the filters can be implemented using the operational amplifier. So, I will see you in the next module. Till then, you take care. Bye.